All right, so if you've spent any time with differential equations, you've probably heard of initial value problems, right? You know where you start, you know the initial speed, and bam, you can figure out the whole journey. But what if you don't know that starting speed? What if all you know is where you start and where you need to end up? Well, that's where things get really interesting. That's a boundary value problem.
Okay, let's break this down. An initial value problem, an IVP, it's kind of like firing a cannon. You know its starting position and the angle you fired it at, and from that, you can calculate its entire trajectory. A boundary value problem, or BVP, is totally different. Imagine stretching a rubber band between two nails. You know exactly where it starts and exactly where it ends. The puzzle is figuring out the shape it makes in between.
And yeah, that string analogy, it's pretty much perfect. Think about a guitar string or maybe a heavy steel beam that's supported on both sides. Those boundaries are just the points where it's locked down. At the start, x equals 0, and at the other end, x equals L. The differential equation is what describes the physics of how that thing curves, whether it's under tension or just sagging under its own weight.
But, what does fixed actually mean in a mathematical sense? Well, it turns out there are a few different kinds of rules or conditions that we can set for these boundaries.
First up is the differential condition. This one's the most straightforward. It just means you're fixing the value of the function right at the boundaries. So, for example, you could say the temperature at one end of a metal rod is held at a constant 20 degrees, and at the other end, it's 100 degrees. Those values are locked in, period. Okay, but what if we change the game a little? With a Neumann condition, we don't care about the temperature itself. Instead, we fix its rate of change. That's the derivative, which physicists call the flux. The best way to think about this is insulating the ends of that rod. If no heat can get out, then the heat flow, the flux, y prime, has to be 0.
And of course, we can even mix them together. A Robin condition links the value and its derivative together. This is how you start to model more complex, real-world stuff, like how heat escapes from a hot pipe into the cooler air around it through convection. It just goes to show how much control these boundary conditions give us. So, we know how to set the rules at the edges. Now, let's get to the part that might just break your brain a little, especially if you're comfortable in the nice, predictable world of initial value problems. With IVPs, you're basically guaranteed to get one single unique solution. So you think the same thing would apply to BVPs, right? I mean, you know the starting point, you know the ending point. There can only be one path connecting them, can't there?
Well, nope. It's not one possibility. It's not even two. It's three.
And this right here is the absolute heart of the matter. Unlike an IVP, a boundary value problem can have exactly one unique solution, which is what you'd probably expect, or it can have no solution at all. Or, and this is the weirdest one, it can have infinitely many solutions.
I know, that sounds completely wild, so let's not just say it, let's prove it. We're going to take one very simple differential equation, and just by tweaking the boundary conditions, we're going to see all three of these outcomes happen right before our eyes. Okay, here's our equation. Y double prime plus y equals 0. The general solution to this is a nice, simple mix of sine and cosine. For our first case, we'll pin the start at y of 0 equals 0 and the end at y of pi over 2 equals 1. So, when we plug in those conditions, the first one, y of 0 equals 0, immediately makes our cosine term vanish. Then the second one, y of pi over 2 equals 1, forces the number in front of our sine term to be exactly 1. And that leaves us with one and only one possible answer, y equals sine of x. Super clean, super simple. Now, let's look at case 2. We are using the exact same differential equation. The starting point is also the same. The only thing we're going to change is the endpoint. We're just going to slide it from pi over 2 to pi. So now we want the function to end at y of pi equals 1.
Okay, so what happens? Well, that first condition, y of 0 equals 0, still makes our first constant, c1, go to 0. No problem. But then we plug in the second condition, y of pi equals 1. That gives us c2 times the sine of pi, which is 0. So the whole equation just becomes 0 equals 1. And that is a flat-out mathematical contradiction. It's impossible. These boundary conditions are asking the equation to do something it physically cannot do. There is no solution.
And finally, we get to the most mind-bending case of all. Same equation, same start at y of 0 equals 0, but this time we're going to demand that the function also ends at 0. So y of pi has to equal 0.
So what happens now? Again, that first condition makes C1 0. But look at the second condition. It gives us C2 times the sine of pi equals 0. Well, sine of pi is 0, so this just becomes 0 equals 0. Now, that's a true statement, sure, but it tells us absolutely nothing about what C2 is. It could be anything. It is completely unconstrained.
And that means C2 could be 1, it could be 5, it could be negative a billion. Any value you pick for C2 will create a perfectly valid function that satisfies both of our boundary conditions. So we don't have one solution, we have an entire infinite family of them, all shaped like y equals some constant times the sine of x.
So what does all this really mean? It means that in the world of differential equations, where you're headed can be just as important and, honestly, sometimes way more complicated than how you start your journey.
The big takeaway here is this. Boundary conditions are not just some minor details you plug in at the very end. They are absolutely fundamental. They can literally decide whether a physically meaningful solution is even possible. As we saw, a tiny change at the boundary can flip the outcome from one perfect answer to complete impossibility.
And remember that broken case with the infinite solutions? Well, it turns out that it's not broken at all. It's actually one of the most important concepts in all of physics and engineering. Those special solutions, they're called eigenfunctions, and they describe everything from the ways a guitar string can vibrate to the stable energy levels of an atom in quantum mechanics. It's a huge deal.
So, that leaves us with one last question to chew on. If something as simple as changing one number at the boundary can completely determine whether a solution even exists, what other mathematical rules that we take for granted might be a little more fragile than they seem? It's a pretty powerful reminder that the context and the constraints of a problem are everything. Thanks for joining me.